Okay. The process of stoichiometry, I have two different scenarios. These are two scenarios that you are going to need to recognize as soon as you read a stoichiometry type problem. And these two scenarios I have listed underlined here. It's one called theoretical yield, right? Theoretical means in theory, means if everything was perfect. And yield means how much you're going to get. So a theoretical yield means in a perfect chemical scenario, how much product am I going to get if this reaction goes to completion? And that definition, you can look that up in your text. You can look that up online. I'm not going to write all of that. I broke it down in bullet points to say that what that means physically is that any other reactant that is not being given to you is going to be in excess. And excess means there's more than enough of it to go around. So if the reactant is ammonium chloride and it's reacting with water, then water is the excess reactant. You don't have to worry about it from a mathematical standpoint. That's what a theoretical yield problem is essentially setting up for us. And that means that all of the reactant of interest, meaning the one that you've been given the information about, all of that is going to get converted. We don't have any left over. In the last lecture, I talked about, hey, how much can you make? How much is left over? In a theoretical yield problem, the reactant of interest is completely consumed, none left. We have turned it into all product. This kind of problem only needs one-dimensional analysis. When I say one-dimensional analysis, I don't mean one step, I mean one calculation. If you write the dimensional analysis properly, you do not have to do it in multiple lines. I know some of you all may do that. I'm going to show you how to not have to do that for each of these scenarios. Now, our molecular weight conversion factor, over there. Our mole-to-mole conversion factor comes from where? How do we compare moles to moles within a chemical reaction? No. Moles to moles within a chemical reaction. What values? The coefficients of the balanced chemical equation. That's where mole-to-mole conversion factors come from. The coefficients of the balanced. And you can't balance unless you can predict products correctly. So, everyone's favorite, seasoning that causes high blood pressure, sodium chloride. This is the process upon which sodium chloride could be made. What type of reaction are we dealing with here? Synthesis reaction, we have two things in elemental form. You got to be able to recognize that off the whams. So we got synthesis. All right. With a synthesis reaction, we need to be creating a compound, and that compound in this case is going to be sodium chloride. And sodium chloride is NaCl, and it is a solid. We should know that from looking at it and having seen it. We've now completed the reaction. We must balance the reaction. Remember that our subscript here means that there are 2 atoms of chlorine or 2 moles of chlorine. 2 here, 2 sodiums. We are now balanced. So our mole-to-mole conversion factor can be formed now based upon the stoichiometric coefficients of the balanced chemical equation. So let's look at A, B, C, and D as it pertains to conversions. In A, the scenario is that I have given you 15 moles of sodium solid, how many moles of product formed? All right, again, I say theoretical yield problems don't talk about the other reactant at all. Notice, nowhere in this have I talked about CO2. And the reason is because there is an excess and we're not worried about its amount. Essentially saying money isn't an issue. What kind of car are you going to get? Chlorine, elemental chlorine is not the issue here. It is in excess. But what that does mean is that all of the sodium is going to get used up. So, again, we need to know which conversion factor to use to get the answer that we want. And we want to be able to go from moles of a reactant to moles of a product. Which one of these conversion factors has to be used? Mole to mole. There's nothing in this question about mass. Therefore, we need not to use this at all. Molecular weight conversion factors involves moles and mass. Mole to mole, because we're being asked to go from mole to mole. So, we write down the information we have, and then the conversion factor that's going to give us the answer. This problem would start with 15 moles of Na, and then the mole-to-mole conversion factor of interest, and I'm going to write it in red since I have it kind of color-coded. What unit and description needs to be on the bottom?
2 moles per 1.
2 mole Na.
For 1 mole of NaCl.
But I want to, before we move to the numerator, I want to make sure people understand why this is 2 moles of Na and not 1 mole as we've seen in the molecular weight conversion.
Because you need 2
Because
moles.
it's by
Well,
the coefficient after
It's based on coefficients of balance equation. A lot of people get confused here. Write 1 because, oh, this is a conversion factor. There are different types of conversion factors. Knowing which one to use is going to make your life extremely easy. If you get to this step and are confused which one to use, obliteration. Surely. Now, we have been asked about product. There is only one product.
NaCl.
Sodium chloride. So we end up with 2 moles of NaCl. Again, 2 divided by 2 is 1. That leaves us with 15 moles of product. Simple, right?
For now.
The easiest one you can get. Mole to mole. You have to be given a number of moles. You have to be able to balance, predict products, and then use the conversion factor, do the multiplication, and then come up with an answer.
And those 2's came from the balance equation.
Yes, that's why I have them in red. And that's why I have mole to mole conversion in red.
All right.
These are coefficients. You could also call them stoichiometric coefficients. That's the proper terminology for it. All right. Let's look at B. B is asking us to go from mass to mole. So the scenario question will be 100 grams of Cl2 is reacted to form NaCl. How many moles of product form?
So 1 mole is 7.91 grams.
35 and 35. Right. But again, even before that, we now have a different scenario. We now have a number of grams. If you remember from our previous lectures, you cannot compare apples to oranges. And grams and moles are just that, apples and oranges. You can only compare apples to apples. And in this case, the apples are the mole. We must get any mathematical value we have into moles to be able to compare it from reactant to product, reactant to reactant, product to product. We cannot go directly from the mass of a reactant to the mole of a product without a conversion factor. And that conversion factor, now that we have involved mass, which one should we be using? We now have a mass. We need to use molecular weight conversion. We have to use a molecular weight conversion factor as well. We cannot go from mass to mole to get the answer we want. We can't because the units won't cancel. So now we need a dimensional analysis that is still one calculation but has multiple conversion factors. So what information do we start with? We need to start with 100 grams of CO2. So to get from CO2 to sodium chloride, we have to be in moles. This is where you must recognize that getting to moles utilizes the molecular weight conversion factor that we just showed how to calculate and how to get over here. We need to get the molecular weight of elemental chlorine, which is 35.45 times 2. 79.1.
70.9.
70.9, sorry, 79. 70.9. 1 mole CO2, 70.9 grams CO2. How do we calculate that? The same way we calculated the total molecular mass over there. This is the same conversion factor. 1 mole over the molecular weight. Notice that this number is not related to our stoichiometric coefficients. This is a different conversion factor. That's why I'm showing which one to use. In here, in B, we must use this one first. Now, some of you all, and that could just be for how you are comfortable mathematically, a lot of you all will want to do this calculation right now and get a number. I'm telling you, for time purposes and for thought stream and the way chemistry thought processes should work, you're not done once you get the moles of chlorine, because that's not what the question asks you. The question wants to know product. Chlorine is not the product. Sodium chloride is. So now we must utilize a conversion factor that can compare moles of reactant to moles of product, and that conversion factor would be which one? The mole to mole. So now we can back the mole to mole right up into our dimensional analysis and show that 2 moles of sodium chloride for every 1 mole of CO2. We have now canceled every unit except the unit of interest. Grams of chlorine, gone. Moles of chlorine, gone. Moles of sodium chloride, left. If we remember how to treat our dimensional analysis as a mathematical situation, we have 200 divided by 71 effectively. This is almost 3, right? 2.82. 2.8. 2.8. 2.8 moles of sodium chloride. So here is mole to mole, one-dimensional analysis, 1 step. Mass to mole, one-dimensional analysis, 2 steps. Where are our questions here? You need to ask them now because I'm moving. Come on. Ask me.
So,
Where-
what do you think the 2 moles of sodium?
This is the mole-to-mole conversion factor based upon stoichiometric coefficients. So, I'm going to label them. You can't, they stay together, right? You can essentially treat these as one whole thing. You can't get to the units of moles of chlorine without the molecular weight conversion factor. And you can't get to moles of product without the stoichiometric coefficient conversion factor, which is based on the balanced chemical equation. Remember, this is a assumed 1. More questions?
So where do you get the 2 from? Multiply the 1.4?
Which 2? Which 2?
So if you do the math right there, it comes out to be 1.4.
This ends up being 1.4, right?
So what's that 2 from? From the product coefficient of?
Yes.
Oh, there.
You can't. Again, those of you all who want to do this first calculation first and then write another dimensional analysis, that's on you. But this 2, this entire entity here is based upon the reaction.
Yeah, but the answer for that equation right there is 1.418, not 2.8. So that's what I'm saying. Where's that other 2?
No. 100 times 2 gives you 200 divided by 70. 2.8. You didn't do this multiplication of the 2 here. It ends up being 1 point something without that 2, yes. But you need to multiply by 2. And then you get 2.8. There's your answer. Again, always double check your calculation, especially on the test. Just double check it twice. I make the mistakes all the time, so. Any questions about this? And I'm about to erase A and move on to C. Again, remember, everything on the top is multiplied and then divided by everything on the bottom.
Actually, wait 1 second. So, if that was a 3, we'll multiply 1.41 times 3 moles.
It would be 100 times 3 divided by 70.9.
Where
Yes.
did the 70.9 come from again?
Molar mass, based on the formula and the molecular weight, based on the periodic table. 35.45 chlorine plus 23. So you gotta look at chlorine's mass plus sodium's mass.
Just to be clear, so for mole, it's molecular weight conversion, and for mass to mole, it's molecular weight conversion in
No.
mole to
For mole to mole, it's only mole to mole conversion.
Yeah, sorry.
And then for B, you're gonna have to use both.
So mass to mole is both.
And C, we're gonna do next. All right. So C is gonna be mole to mass. Let's say I give you a number of moles to start with. 0.73 moles of chlorine reacted. How many grams of sodium chloride produced? Notice that I'm asking these in different ways each time. I'm throwing in words that are different each time. These are all trying to help you recognize what are the key words in the problem that tell us which direction we need to go. We've been given moles of a reactant. We've been asked about mass of a product. We need to be going from a mole to mass conversion, which I have listed here as C. You know, you could be asked about any one of these 4. So now we are starting with number of moles, and to get number of moles, 0.73 moles of chlorine. To get moles of a reactant to moles of product, what conversion factor do we use?
Mole to mole.
We need to use mole to mole. Again, we already are in the apples, if you will. we don't need to do molecular weight conversion in this step because we need to get to sodium chloride. So our dimensional analysis is 1 mole of Cl2 to 2 moles of NaCl. Hopefully this clicks. This example should right now, okay, we got moles, we need to be using mole to mole if we're talking about product. If we do the calculation right now, what is our answer going to have as its units?
1.4 moles.
Units.
Moles.
Moles of
Sodium
product. Is that what the question is asking us about?
No.
So we're not done. We're not done. But how do we relate moles of a compound to mass of that compound? Like the weight conversion factor. So we've effectively kind of flipped the thought process, but we're using the same conversion factors. Sodium chloride, 1 mole of NaCl is equal to 70.9 grams NaCl.
No.
No,
That's
Oh, not 70.9, you're right,
58.
58, excuse me, yeah, 58.44. Sorry, I was using the molar mass for chlorine. 58.44. Again, those of y'all who are not sure where these molar masses are coming from, that's where part 1 and 2, or part 1, is going to be very helpful. Calculation of molecular weight utilizing the chemical formula. So we got essentially 1.46 times 58.44. 85.3. 85.3 grams of sodium chloride. So in this example, C, we given a mole, we must go to moles of product and then go to mass of product. In the previous example, we went from mass of reactant to mole of reactant to mole of product. Being able to recognize the type is going to be very important. And then you should be able to, the main process here is to understand what the next dimensional analysis blocks should have in it. And then you should never be lost. Because you know that this needs to say mole of chlorine, because otherwise we can't move forward with cancellation. So you should never be confused about what's on this bottom block. The question, it should always be that.
Yeah.
It should always be that. The question about the top, you can deduce from what is being asked of you.
Okay. So that's a rule. Always.
That's a rule for any kind of math conversion.
Oh no.
Yeah, any kind of math conversion. You can't get rid of a unit unless you are dividing by that
Yeah.
unit.
Okay. Units are very important.
Right, units are very important in everything, right? That's all the what was it? U.S. Was it U.S. or Europe? Somebody converted incorrectly from English to metric, sent a multi-million-dollar satellite into space, and it missed. Yeah,
Russia, wasn't it?
I don't know.
Maybe. NASA.
It was now. I was about to say it was American.
NASA, China, and Japan combination.
Right. Yeah. Right. Bad math. You wouldn't want anybody messing up your hourly wage conversion. Why is my check $3? Well, I thought you only got paid 30 cents an hour, not $30 an hour. Exactly. Same thing. All right, last but not least, obviously, the most complicated one. Mass to mass. Starting with a mass of a reactant and then finding a mass of a product. So, our question indeed would look like 6.74 grams of sodium reacted with excess Cl2. How much NaCl formed in grams? All right. Starting with the mass of a reactant, we want to get the mass of a product. We need to write down first the information that we want. Then we need to realize that the next conversion factor needs to have grams on the bottom. The conversion factors that have grams on the bottom are the molecular weight conversion factor. We need to get the moles anyway to be able to compare anything. So this should be 58.44 grams of sodium per 1 mole of sodium.
Is it 23.9?
Sorry, 23. Yeah, I'm trying to use the other numbers instead of calculating. Let's go too fast. 22.9 or 23. Generally, you see sodium rounded up. The 0.9, anytime it's a 0.9, you can normally round.
That's acceptable.
That's acceptable. A 0.9 is, but not a 0.8. 0.7, you normally want to keep it. But generally, sodium is rounded, and what's the other one that's normally rounded? Carbon?
Oxygen.
Oxygen. Yeah, oxygen is normally rounded to 16. Yeah, that's what it is. All right, so now we have moles of sodium. We cannot go from moles of sodium to what we are being asked for. You can't go from moles of one reactant to the mass of a product. What you must go through first is moles. So now we need to use the mole-to-mole conversion factor. That tells us that 2 moles of sodium go with 2 moles of sodium chloride. Stoichiometric coefficients. But we haven't been asked about moles of sodium chloride either. We have been asked about mass. We went from a 1-step problem to 2 2-step problems. Now we have a 3-step problem. Still can be done in the same dimensional analysis. We must use, once again, the molecular weight conversion factor to get us back to mass. There's only one way to get us back to mass. Molecular weight conversion factor says that 1 mole of sodium chloride is 58.44 grams of sodium chloride. And there is our dimensional analysis for a mass-to-mass theoretical yield problem for this synthesis reaction. So it's going to be roughly 12.
17.
23 divided by, ends up
17.
17. 17.1. Okay. 17.1 grams sodium chloride. Again, if you are unsure, you can always check if your units cancel. If your units do not cancel in your dimensional analysis, regardless of the order, then it's going to be wrong. Almost 99% of the time. Grams of sodium gone. Moles of sodium gone. Moles of sodium chloride gone. Left with mass of chemical of interest. And the chemical of interest may not always be product. We'll see some examples where it's not always. You might be given product and asked to find out how much reactant was reacted. It's no different in the process. Still the same math, except you're trying to find out how much product was consumed. All right, any questions about A, B, C, and D? That example has covered all different types. That is not the only reaction you can do this with, right? And if I have some time after I finish limiting reactant, because I have to get to that, if I have some time, I'll do maybe 1 or 2 examples. I'll put an example up, let you work through those, convince yourself you know how it's done. But any questions about C or D? We went molecular weight conversion to mole conversion, back to molecular weight conversion because we were asked to convert mass to mass.